University of Arizona, and we'll be talking today about logarithmically correlated fields from non-Hermitian random matrices. Okay, thank you, Giorgio, for coming up.
Thanks, Suner, for the introduction. So yeah, today I will present like some fairly natural like log-correlated fields that come up in non-Hermitian matrices, and I will first start with a fairly substantial like introduction and motivation, like of what kind of questions and maybe why one would like to study these log-correlated fields in this setting, and then we'll go more into the connection with random matrices. So yeah, feel free anytime to interrupt that is not clear or any questions and so on. Okay, so let's start with log-correlated field in general. Let me just briefly, like, relatively informally define what do I mean by log-correlated field. Maybe not so surprising by the name. Is that it's a stochastic process that is denoted by this X, Vn here, and Vn is say a metric space. Just think to be Rd or whatever metric space you want, and then it's called logarithmically correlated because this stochastic process is Gaussian and is characterized by the following covariance, so which is basically diverges logarithmically with the distance of the two base points, say V and V prime. And here I put this n here, this regularization 1 over n. You can think of n to be a large number, but fixed in such a way that everything is defined pointwise, because if I would not put the 1 over n here, when if the distance goes to 0, then the variance pointwise will not be defined. So that's that will be regularization 1 over n basically throughout the talk. Okay, and this is important. Doesn't have to be an exact equality. It's just important leading order here. So lower order term in n are allowed. Okay, so that's what a log-correlated field is. So let me maybe write down some motivation why, both from a mathematical physical point of view, it would be interesting to study these log-correlated fields. So the first fact is that for these log-correlated fields, the randomness contributes at all scale equally. So maybe the best way to see this is with a fairly simple example, which is the random wave model on the circle. So it's this x theta n, which is the following sum. Again, I mean, we truncate the sum just to make sure that everything is convergent. And we just have like IID Gaussian, this nk, 0, 1, a standard Gaussian independent, and then square root of k, and then there is just a phase factor. And this you can see that, in fact, the contribution, like say for the variance or the covariance, comes from all scale, because if you compute, say, the variance of this quantity, well, it's nothing else than the sum of 1 over k. So it's like the, let's say, Taylor expansion of the log. So that's precisely why all the scale contributes, because we have a divergent sum, logarithmically divergent sum. So that's why log-correlated field, and that's why all the scale contribute. Okay, more from maybe more on the statistical mechanics side, like one reason is that if you look at the Gibbs measure e to the minus beta x, where x is a log-correlated field and b is just a fixed number, the inverse temperature, then these log-correlated fields are like one of the simplest example exhibiting like one-step replica symmetry breaking. Maybe.
Giorgio, may I ask you a question?
Sure.
So you mentioned this random wave model. So is it somehow a nice way to think about this logarithmic correlated fields, or is just more like academic model? Or
Yeah, this is probably one of the. It's more of a simplest example, one among the simplest example that it's a log-correlated field. I mean, several log-correlated fields you can write in this way, or approximately in this way, as we will see also later, but like not necessarily. So they're not all look the side like this, but like, so this one is, yeah, it's a simple example to see.
Okay.
Yeah, thanks. Thanks for the clarification. Any further questions? Okay, so I was saying, yeah, this is among the simplest. Maybe the simplest one is the random energy model, but like, okay, maybe the second simplest then. Okay, so let me mention a third reason why maybe one wants to study these logarithmic fields, or in particular the I points, is that one has been shown that the logarithmic fields, in particular the Gaussian free field, I will show that later, are fundamental building blocks to construct the underlying measure of the two-dimensional Liouville conformal field theory. So let me very informally write down how this measure looks like for the Liouville CFT, which is basically the exponential of the Gaussian free field. So gamma is a coupling constant. You can think to be a positive number. Doesn't have to be too big, but let me not go into that. And the point here is, again, that X is at the Gaussian free field, so in particular as a log correlated field. In fact, later we'll see that the Gaussian free field is in fact log correlated, maybe not so surprisingly in 2D. And so since we have this exponential measure, one can see basically that this measure is supported. First of all, it's supported on I points because, well, we had exponential, so that's the one that matters. So that's one reason why one would be interested to study these I points of X. And this measure, our connection is called like the Gaussian multiplicative chaos measure that was introduced by Kahn like in the 80s. Okay, so these are the three same main motivation. And now I want to explain like the kind of questions that we're going to look at, like also from the random metric side, with some examples to see what are the features of this log-correlated field, and in particular of maximal value of these log-correlated fields. Okay, so maybe the simplest example is to consider a branching random walk here on a binary tree. And on each of these edges, we have the standard Gaussian random variable, real Gaussian random variables, which are denoted by y. And then we look at our x, so our field is going to be the sum of all these increments. Like, so we pick a point here at the base of this tree, and then we start from the root and take the sum of all the paths that we have to take, like to reach this V. So in particular, for this concrete example, we start from here, then we take this one, and so on and so forth until we reach V. And so for fixed V, this is just basically a normal random walk, and this branching structure comes if you look at the correlation of two different points, say V and V prime, and we look at the corresponding increments. So you can see that, so if L here is, so that we look at the L step where L is smaller than this guy, so V wedge V prime, which is the last common ancestor. So in fact, if you look at V and V prime, this is the last point where they share this edge, and then they branch. That's why branch random walk. So for the increments before this last common ancestor, they're perfectly correlated. In fact, it's the exact same Gaussian random variable. And then at this step, at this point, they branch and the increments will be independent. So that's why we get 0 here. Okay. So this is, as I said, one of the simplest examples to keep in mind, but it will come back very often in the following, because in this case, one can compute fairly several things explicitly, and so that, as we will see, basically the general strategy for more complicated cases is going to be to exhibit some sort of or approximate branching random walk representation, and then use techniques like known for branching random walk to get the desired result. So I will go into more details later. So let me go a bit more into the details to see which question I want to study now. And let's do this with another example, which is, for example, the branching Brownian motion, which is basically a continuous version of the branch random walk. So we start with a Brownian motion, and then at a random time, which is exponentially distributed, this splits into two different Brownian motions, and so on and so forth. So we look at this up to a certain time t. So it's this t here, which is a fixed large number. And one can see that the branching Brownian motion is log correlated with respect to this distance. So again, so t is a fixed large number, and v wedge v prime is the same as before. It's like the last common ancestor. If we take this time horizontally, we take v and v prime on this line, and then the last common ancestor is the point where the Brownian motion branched. Okay, I mean, this is not quite a distance, like if you check, in particular, yeah, check v equal v prime, like, but it's almost like, so close enough. Okay, so the first thing I want to say about the seminar result by Bramson in 78, we studied the maximum of this branch Brownian motion. So basically the highest points here that it will reach. And this was motivated from, say, the study of the solution of FK, KP equations, that one can see that basically the solution can be given as the probability that the maximum is smaller of this branch Brownian motion is smaller than a certain t. And what he showed in this seminal paper is at leading order, the maximum is linear, so it's given by t. So even though each Brownian motion is diffusive, so it's based on a scale square root of t, then since we have many of them, exponentially many, the maximum behaves linearly. And then, interestingly, also computed the subleading order correction here, which is this 3/4 log t. And I highlighted this the 3/4 in green because while the log t is maybe not so surprising, that's very natural, this 3/4 it is quite surprising. This is because, for instance, if we compare with the Gaussian independent case, so if we just look at exponentially many Gaussians with variance t/2, independent Gaussians, then the maximum will be a leading order the same, but the subleading order will have a 1/4 instead of a 3/4. So this 3/4 is a consequence of the correlation of the log correlation of the fields. So in particular, we will see later on, and one can expect that one can use this 3/4 to identify the class of logarithmically correlated fields, so that for many logarithmically correlated fields, maybe one can prove that they fall in the same universality class, in the sense that they have the same coefficient here. But more is true, like in fact, this we will see in the next slide, like this universality, this expected universal behavior also will appear at the next order. So far, here, everything, I mean, this approximation here is everything is deterministic, so one can ask what happens on the fluctuation level, so what on the fluctuation of the maximum. And to look at this, we look, for example, at the two-dimensional discrete Gaussian free field, so yet another example, and see what one can say again about the high points of this field. So the discrete Gaussian free field here, just say with Dirichlet boundary condition, is a Gaussian vector X, which is which has the following distribution. So it just dn is a normalization constant, and then is the distribution of X is given by the following Gaussian measure, where this tilde here, it means that it's a nearest neighbor interaction. So it's v and v prime close to each other. And okay, this is a log correlated field in 2D, just with respect to the Euclidean distance. So again, now we can ask, if we look at the high points, do we expect a similar behavior? So for instance, do we get again this 3/4, and like what can we say more? And in this very nice result by Bramson, Ding, and Zeytouni, they show that if we properly normalize the maximum of this of the Gaussian free field, then we get the following asymptotic expansion. So the first two terms you see are basically the same as in the branching Brownian motion, just replacing t with log n. And again, the first term behaves linearly log n, the second order is a log, and again comes precisely with this constant 3/4. And then here Zn, it's an order 1 random variable which converges in distribution. And in particular, they showed in this result that this Zn, or the limiting distribution of Zn, has the following tail behavior for certain values of lambda. So in particular, it has behavior is like exponential times lambda, which shows again the difference with respect to the independent case. So for instance, if you have independent Gaussian, then the fluctuation of the maximum will be Gumbel. So that's, I mean, one can associate Gumbel with independence, basically, and if the tail is light enough. Instead here, again, as an effect of this correlation, one gets a different tail behavior. Again, which is expected to be universal. So at the beginning of the talk, I promised that actually, even if not obviously, like behind many of these results, there is some sort of branching random walk representation or branching random walk structure. And in fact, this is the case also for the GFF. In fact, on a very high level, I mean, there are several complications and difficulties along the way, but like on a very high level, the way they compute this maximum is by exhibiting a underlying branching structure also for the Gaussian free field. So let me just explain it quickly in words, is that rather than, if here we're interested in the, say, the value of the field and a point, but rather than looking at this value itself, we look at the value at that point minus the value of a box around that point, and then plus the value of this box minus a larger box, twice a large box, and so on and so forth. So basically, we can express the value of a point as increments over the values of boxes of each one being twice as large as the previous one. So basically, we see the values averaging over basically log n boxes. And one can see that this gives a branching random walk representation. This gives a branching structure. And the branching comes from the fact that if you have a box, then basically if you get 2 points V and V prime within the same box, then you can expect this to be correlated on that scale. And then if one of them is outside, because of the marker property of the Gaussian free field, like the value inside the box is not sensitive about what happens outside. So they're independent if they're outside. So that's where the branch random walk appear. Again, I mean, I don't want to go into the details, but the main message is that also to prove this result for the Gaussian free field, where in principle there is not obvious branching structure, one can find one and then capitalize on this to get this result. Okay, so this is like the main motivation, which kind of questions like we're interested in, and now I want to explain what's the connection of random matrices, what has been known. So we start with the one-dimensional case that it's better understood. And then I will discuss higher dimensional cases. Okay, so if there are any questions, a good moment, like before I move on. And, okay. So,
sorry, Giorgio, maybe I have a question.
Yeah.
You allow me to. So, so I was just trying to understand the branching structure of the GFF.
Mhm.
So uh, just from a heuristic point of view, is it okay to think about just dividing the GFF is more or less like dividing a big square in smaller squares and sampling exponentials, sorry, Gaussian random variables there and keep doing that?
Yeah, something like that. Yes.
Okay.
Mhm.
Okay, thank you.
Any other question? Okay, so let me now explain like historically like where this connection of random matrices and logarithmic fields started. Actually goes back quite a while. And the simplest example to observe this connection is the circular unitary ensemble. So which is basically just unitary matrices that are drawn according to their measure. And the spectrum of this matrix here is just a underbanded matrix. It's given by, is supported on the unit circle because, well, the matrix is unitary. So that's how it looks like. And one can see that the distribution of these eigenvalues of the omegas, or I mean eigenangles, it's explicitly given by the following, basically, van der Monde determinant. And here, beta, it's a parameter that in the unitary case, it's equal to 2. That's the circular unitary ensemble. But in general, one can consider more general ensembles with different betas. And this will be relevant in the next slide because I want to stress like how this depends with beta. So for example, the beta equal 1 case would correspond to the case of orthogonal matrices instead of unitary matrices. And so, I mean, this beta is nothing else that a parameter that determines the the level repulsion, the repulsion between two nearby eigenvalues on the circle. Okay, so the first question is that okay, we are on the matrices where we have to find a local-rated fields. What's the natural candidate? And well, the natural candidate is the log determinant. So the claim is that if you look at the log determinant of our matrix U minus I theta, where theta is just something between 0 and 2 pi, then this is a log correlated field. And this is in fact the case. So one can show if you look at this log determinant at different points, theta 1 and theta 2, then one can compute this covariance and it's given as follows. So in particular, you can see that if theta 1 and theta 2 are close to each other, then basically we can Taylor expand the exponential, and this behaves like the log of the difference of theta 1 and theta 2. So these are log correlated fields. Here I wrote down like two references because so this result in a distributional sense was first computed quite a while ago by Dawson and Mehta, and more recently Diaconis and Evans proved this pointwise for fixed thetas, theta 1 and theta 2. Okay, so now we have a log correlated fields, and then the question that were raised like a while ago, that I will go into that in the next slide, is like how the maximum of these log correlated fields behaves. So I will state this. So this is what is known as the Fyodor-Yarek-Keating conjecture that I will write down in a moment. So let's consider e to the I omegas, which are C beta eigenvalues. So by that, I mean just that the e to the I omegas are distributed according to this distribution for some beta. And then we again look at a version of the characteristic polynomial that's denoted by xn of theta, which is the nothing else the product of these eigenvalues minus e to the I theta. And in a beautiful conjecture in 2012, Fyodor-Yarek-Keating conjectured that this log determinant of unitary matrices, in fact, falls in the universality class of logarithmically correlated fields. So precisely in this paper, heuristically, they computed and like conjecture that if now we look at the maximum of the log of this xn, the absolute value, now the maximum is over the unit circle, then we have the following asymptotic expansion. So the beta here, which represents this repulsion between nearby eigenvalues, appears as a prefactor here, like 1 over beta. And then apart from that, you can see that we get exact same asymptotics as we got for log-correlated fields, like for branching random motion or Gaussian free field. So that we have this 3/4 appearing here, and then for Zn, again, they expect it to be random variable, order 1 random variable converging distribution to the sum of 2 independent Gumbel. Actually, the fact that it's explicit independent Gumbel was figured out by Subak later. But I mean, again, the point here is that if you write down the computation, one can see that the tail behavior of the sum of 2 independent Gumbel behaves exactly as lambda times e to the minus lambda. So it's again, this Zn, they conjecture to have the same tail behavior as the limiting distribution appearing in the maximum of the Gaussian free field. So I should say that I stated this FHK conjecture for unitary matrices because my main interest is for random matrices, but like in the same paper, they have like together this conjecture for unitary matrices and for the Riemann zeta function. So they conjecture that if you look at the log of zeta over the critical line, and we look I up on this critical line, so what I mean is that, so here u is close to tau, it's an order 1 interval around tau, and tau it's a uniform distribution over t to t, say, and t it's a very large number. So if we look I up, and then we look at the maximum, again, we would expect asymptotics exactly like this one. Again, with the proper replacing log n with some function of t, log t, or log t. But again, you'll see the 3/4 appearing and the tail behavior of the leaping distribution in the zeta case also expected to be the same. So in particular, yeah, this is what I just said, while the actual distribution of Zn is expected to be model dependent, for example, for the Riemann zeta function is expected to depend on the small primes, the tail behavior is universal, so it's expected to have this universal tail behavior. And I should say, even though I will not say anything more about the zeta function, is that in a couple of papers, there's some breakthroughs about zeta by Bourgade and Ratsfield, where they can basically compute the maximum of zeta up to tightness. And they can even give an estimate of the tail behavior, showing that, in fact, it's consistent with this. Okay, that's the only thing I want to say about zeta. So let me now instead show you what is known for unitary matrices. So in fact, actually quite a lot is understood for unitary matrices in the one-dimensional case, is that one can show that if you look at the maximum of this, the log of the characteristic polynomial, after we properly center, yeah, I shift by C just to have a center Gumbel, I mean, center random variable Z. Then Paquet and Zeytouni show that if we properly center, then this converges to a under 1 random variable, which is the sum of 2 independent random variables, and one of them is a Gumbel random variable. So this doesn't quite show the Fyodorov-Yarkin conjecture, because that would amount to show that both of these independent random variables are Gumbel, and I can show that only one of them is. But one thing that I want to stress is that while this recent result proves a large part of this conjecture, actually this it was like cumulative effect, like cumulative result of many previous partial results. So basically, this expansion here on the right and on the left-hand side has been computed like term by term. So first with the log n, then the log n, and then the tightness, and then finally in this recent work by Paquet and Zeitouni, the convergent distribution, but it took quite some time. And again, one thing that I want to highlight, I mean, I'm not, of course, not going to the detail of the proof, but like that all these results that I mentioned here, and even the one by Paquet and Zeitouni, they, in a way or another, they exhibit a sort of underlying branching structure. So where this branching structure comes from? So we're interested in saying the unitary case for simplicity at the log determinant of this unitary matrix. So, well, let's one can just write the Taylor expansion of this of the log. So it looks like this. So we have the trace of this unitary matrix to the power k divided by k, and then we just have this phase factor. So if you look at it already, this looks pretty similar to the random wave model that I showed you in the previous slide, except that in that case, instead of this trace of uk over k, we had standard Gaussian divided by square root of k. So it looks similar, but like not quite yet. It would be if we can show that this trace of uk are in fact, at least asymptotically, independent Gaussians of variance k, because then this would be exactly like the random wave model. And this is in fact the case. This was shown by the Diaconis and Shashani, where they computed arbitrary I moments of unitary matrices. And in fact, they showed that if you look at the family of this trace of uk, then it converges to independent complex Gaussian such that the variance is exactly k. So if we plug in this information, basically, if like naively we replace trace of uk by a Gaussian divided by a Gaussian times square root of k, then we exactly get the random wave model. I mean, this is the I want to emphasize that this is just the starting point. I mean, then there are like many difficulty and complication and very delicate analysis like to get this proved. But like the starting point is again finding a branching random walk representation, a branching structure, which in this case is given by basically the Taylor expansion of the log. Okay, and I should say that for the one-dimensional case, so for Wigner matrices, which are just Hermitian matrices with independent entries, or beta ensembles, then also the leading order is known. And under additional assumption for this Wigner matrices, one can compute even more, but I don't want to go into that. So the main message here is that in the one-dimensional case, specifically in particular the unitary case, quite many things are known. Maybe not yet the full distribution of this, but like one can compute all asymptotics and prove the convergent distribution. So, and as well for zeta function. So let me now go in the 2 and maybe 3-dimensional case, like also focus on 2 cases and show you that actually the situation is much more complicated and much less is known. And however, on the other hand, it's a very natural and interesting, in my point of view, like to study the connection of random matrices is like higher dimensional local-correlated fields, because these are what naturally appears in this, say, Liouville conformal field theory, or like even if you look at some dynamics on the Liouville Langevin dynamics, say, on Liouville quantum gravity, then we get, say, 3-dimensional local-correlated field. So can this be reproduced, like also, they have a counterpart in random matrices? And the answer is gonna be yes. And the model to study this, one of possible models, like the one I'm interested in, is like non-Hermitian matrices. So let me just like write down what is the class of matrices that I'm gonna look at. So are n by n non-Hermitian matrices that I will denote by x, which are just n by n matrices with IID entries that could be complex or real. And they are normalized in the following way. So we have an atom variable chi, which is centered with univariance and has all moments. And then we rescale by square root of n. And this rescaling by square root of n is just to make sure that in the larger limit, the spectrum stays typically order 1. And just for notational, like trivial notation, like on name. In the case when this chi is Gaussian, I'll call it the Geneva ensemble. So Gaussian matrices with Gaussian entries I call the Geneva ensemble. So here I just show you the spectrum of two, say 300 by 300 matrices. I put two pictures because on the left-hand side is a spectrum of a matrix which has real entries, and on the right-hand side, the matrix that has complex entries. So if we look close to it, we can see a first important difference is that if you look in the real case, the spectrum is symmetric with respect to the real axis. So you can see that if we have a complex eigenvalues, then this comes with a companion, which is its complex conjugate. So the fact that on the other hand, I want to say that, like, okay, if you look close, we see a difference, but if you look from farther away, like from distance I'm at, then, well, these two pictures looks pretty much the same. I mean, the eigenvalues fill in the unit disk. So, and this is known as the circular law. So basically, if you look at the empirical measure of the eigenvalues, this converges to the uniform distribution over the unit disk. And since we have n eigenvalues in an order 1 subset of the complex plane, one can expect that the typical fluctuation scale, the typical distance between nearby eigenvalues, it's 1 over square root of n, 1 over square root of the dimension. And one last thing that I want to mention that it's related to the symmetry that will be relevant maybe at the end of the talk, is that there is another interesting feature in the matrices with real entries, which is that there is an accumulation of square root of n eigenvalues over the real axis. I mean, I don't know how clear it is from the picture, but like you can see that if you look on the left, you can see there are some points here, like on the real axis, instead on the right-hand side for complex matrices there are not. This with probability 1. Okay, so this is how the spectrum looks like, and then now we want to see what's the natural candidate from the low-correlated field that describes basically the fluctuation of these eigenvalues. So not surprisingly, it's going to be again the log determinant. And in a seminar result by Rader and Virag, now a while ago, they show that for complex Gaussian matrices, then the log determinant is in fact a log-correlated field. So if we look at the covariance of this log determinant different points Z1 and Z2 in the disk, then this is going to be behave like the log of the distance. Again, there is some regularization, but it doesn't matter. So I just studied this a bit heuristically just to highlight this behavior. Maybe let me just say that actually this is proven in distributional sense. So in the following sense, that if we look at some fairly smooth linear statistics of the eigenvalues, here the sigmas are the eigenvalue of non-Hermitian matrix X, then the covariance is given by the following quantity.
Giorgio, may I ask you a question?
Of course, yeah.
I may have lost something, maybe I lose something, but so there is no scaling on this theorem of Ryder and Virag, or you already scaled things.
That's right. So there is no scaling because, I mean, actually, this can be seen maybe even better in this smooth case. Say for this linear statistic ln of f, then this is the difference of two order n quantities. So like, because I mean, f is typically order 1 and we have n eigenvalues. So is expectation. However, basically also what this display below shows is that the difference of two order n quantities fluctuates on an order 1 scale. So this you can find surprising because, so there is no scaling. I mean, usually in a CLT scaling, you would expect a square root of n scaling. Instead here, it doesn't appear because the eigenvalues are very strongly correlated. Okay. So, and this manifests again in the log determinant case, again, like you don't need any rescaling. I mean, you have to center, so you have, but then the variance is given by this log of the difference without any further rescaling.
Okay, thank you.
Thanks. Yeah, this it's a good point. Important to clarify that this unusually small behavior, this unusually small fluctuation scale comes from the correlation of the strong correlation of the eigenvalues of nearby eigenvalues. And well, one can see that if we plug in, for instance, f and g to be the log, then we get back the answer above. Okay, and let me just briefly go through a bit of history, study this kind of question. So this convergence to a Gaussian field was actually first proven by Forrester in 1999 in the special case where f is a radial test functions, and then more recently, with Tertuliano and Schroeder, we proved that the same result does hold not only for complex Ginebra matrices, but for general IID matrices, for matrices with IID entries, but general entry distribution. And maybe one cute fact that I want to mention is that for general matrices, the variance here, there is an additional term appearing in the right-hand side here that depends on the four-cumulant of the entries, which is, of course, not there in the Gaussian case because the four-cumulant is 0, but in the general case is there. And in a different direction, this result was also extended for more general normal matrices by these people in a couple of papers. Okay, so this shows the emergence of a two-dimensional field, and the question is that can we also see the emergence of a three-dimensional field? And that's what I want to discuss because I think it's very interesting and like was not known before. So we look now, instead of consider a fixed non-Hermitian matrices, we look at some dynamics on the non-Hermitian matrices with, for instance, the Ornstein-Uhlenbeck flow, which is defined in here. And this because I look at the Ornstein-Uhlenbeck just because the equilibrium measure is the Gaussian one, so it's the Ginebra ensemble. One can choose different flows, doesn't really matter. And in a very recent, fairly recent paper with Bourgade and Wang, we prove that now the log determinant this time has a three-dimensional process, 2 + 1 dimension. So we look at, depends on z on the disk and on time. It's also a log correlated field. And this time with respect to the parabolic distance. So again, in particular, it's linear in time and quadratic in space. So you can see that if we plug in t equal s, we get back the result by Rader and Virac, but in general, there is this additional term here that I write in green. And again, this is also in the sense of distribution. So I have a few comments about it. So the first thing is that actually, unlike the previous result, like this was not known even in the Gaussian case. So if we have, say, complex Gaussian entries or real, this result was not known because the result by Rader and Virac relies on some explicit determinantal structure, which is available in the complex Gaussian case or in the also known in the real case, but there is no space-time explicit determinantal structure for the joint correlation in space and time of these eigenvalues. So that's why it was not known even in the Gaussian case. And this limiting covariance here appearing on the right-hand side, you can see that has the same regularity as the two-dimensional additive stochastic heat equation. I mean, it's not explicitly the same covariance, but just it's the same regularity in space and time. So the Edward Wilkinson universality class. And lastly, quite interesting fact is that I should mention that this limiting Gaussian field, the limiting Gaussian field of the log determinant happens to be not Markovian. Okay. So now that we have these 2- and 3-dimensional fields, now it's natural to ask what if we look at the I points at the maximum of this field, if they fall again in the universality class of logarithmically correlated fields. So from now on, I just consider the two-dimensional case for concreteness, and one can ask all the same questions for the this 2 + 1 dimensional case, but I won't do that. So we look at the center log characteristic polynomial, so again, the similar quantity, which I call psi n of z. And now we can formulate a non-Hermitian analog of this Fyodorov-Yarekitin conjecture if we look at the maximum of this field. So naturally, now we look at the maximum over the whole unit disk, because the spectrum is supported on the disk for this non-Hermitian matrix, and then one can conjecture the following expansion. So again, the 1/√2 is just a prefactor which comes from the being in 2 dimensions versus 1. But apart from that, we see again we would expect the same asymptotic expansion here. Again, the log n, the 3/4 log n, and then Zn, which is one would expect that it's an order one to converge an order one random variable, but there is no conjecture even in the heuristic level of what the limiting distribution should look like. I mean, one would expect the similar tail behavior as in the one-dimensional case, but this is not known. Maybe one thing that I want to stress here is that if you remember for unitary matrices or orthogonal matrices, the answer will be different. There is this beta parameter that would appear in the one-dimensional case. Instead, in this two-dimensional case, I'm claiming that, or conjecturing that there is no dependence in the real and complex matrices. That if you look at the maximum of this psi over the disk, then the answer is going to be the same, at least for these first two orders, in the real and complex case. And I will try to briefly explain that in the last part of the talk. And in a recent work we did, like with Ben London, the first step to understand this non-Hermitian Fedorov fitting conjecture, which is to compute the first order term. So we could compute that both for real and complex matrices, the maximum is given by the log n over square root of 2. So there is, again, no difference for real and complex, and is given by this quantity. So previously, this result was known only in the special case when the entries are complex Gaussian, and in a nice paper by Gauthier Lambert 5 years ago. So in particular, even in the case when the entries are real Gaussian, this was not known, because while also for real Gaussian matrices, the correlation function of the eigenvalue is explicit, it's very involved because of this special role of the real axis. So that's why this was not known. So as a consequence of our result, we also show these asymptotics for real matrices. And while if you look at the maximum over the whole disk is the same, we do see a difference between real and complex case if we look at mesoscopic slices. So instead of looking at the maximum over the whole disk, we only restrict for points with a fixed imaginary part, n to the minus alpha, where alpha is something between 0 and 1 half. So if alpha is 0, we are back basically to this case, and if alpha is 1 half, it basically corresponds to just look very close to the real axis, and then these are all cases in between. So we investigated this exactly because to see that at first it seems that there is no difference between real and complex, but if you look at this more refined question, there is a difference. In fact, the answer of the maximum over these slices in the real case does not depend on alpha. Actually, this is quite surprising. We don't really have a good explanation why this is the case, but it seems that everything is tuned like perfectly so that the maximum is always the same for any alpha. In the real case, instead in the complex case, naturally depend on alpha. So this is the difference. Okay, so maybe in the last 2-3 slides I have, I just want to give a brief sketch of the proof. I just want to highlight basically what are the main ideas here and how we get this branching structure. So yeah, the first questions I want to answer is how do we get a branching structure? I mean, if you look at this log determinant, there is no obvious branching structure. So in the unitary case, we could do Taylor expansion of the log, but here this is uncontrolled. I mean, there is no, especially in the general, when the entries are non-Gaussian, there is no way that one can control anything like that. Instead, we rely on the Dyson-Barnard motion. So I will just briefly explain basically how do we do that, and then I will conclude. Okay, so the first step to study this log determinant is to use Giorgio's formula. I mean, this is kind of a standard backbone in the study of the spectrum of non-Hermitian matrices. So what is this Giorgio's formula? Well, I mean, it's actually at this level, it seems almost a trivial identity, which is basically, if you look at the log determinant of our non-Hermitian matrix X, this can be written as 1/2 the log determinant of the absolute value square of x minus z star. So, I mean, this is, it's a triviality, but actually the consequences are very important, because now if you look on the left-hand side, this involves statistics of non-Hermitian eigenvalues. Instead, on the right-hand side, we have statistics of Hermitian eigenvalues, which makes which are more easily understood. I mean, it's still hard, but like it's better. So in particular, this log determinant of x minus z star can be written as the sum of this log of lambda I z, which lambda I z being the singular values of x minus z. Okay, so this second step, I mean, it's not relevant, but like I want to say that for understanding the branch structure, but I want to say that actually, rather than looking at the log determinant, this psi n of z, for our original matrix X, it's more convenient to look at this quantity here that depends on time. So basically, here the lambda I z are the singular values of this matrix here. So which is our original matrix X, and then we have the square root of t times Ginebra matrix, the Gaussian component. Here t is just little of 1. And this is, why do we do that? Because this is naturally how the Dyson-Maria motion emerges. In fact, we can see, I will show you in the next slide, that the singular value of this xt minus z are a solution of the so-called Dyson-Maria motion. And why can we do that? Because there is a nice comparison result for extreme statistics by Landon, Lopato, and Marcinek, where they show that actually as long as t is not too big, then the maximum of this psi n, depending on t, is the same as the one at time 0. So yeah, the main message in step 2 is that instead of looking at text, basically you can look at the singular value of this xt minus z. And one can see by second order perturbation theory is that the singular value of xt minus z are the solution of the Dyson-Maria motion, which is a system of couple as this that I wrote down here. And the BIZ for fixed z are just standard de Brownian motions. However, if you look at the correlation of different z1 and z2 that we need to do in a second, then, well, we see that there is actually a dependence on the singular vectors of x minus z1 and minus z2. So this is a fundamental difficulty here. And the point is that, again, I mean, the precise form doesn't matter, is that using the Dyson-Maria motion, we can write this psi n of zt as the sum of this ykz. And the explicit form of the yk doesn't matter, but I want to say that is some like short time increments of Brownian terms, which are very explicit that I wrote down here. So again, I mean, the explicit form doesn't matter. The main point is that one can see, be a bit clear in the next slide where I wrap up, is that this representation here is in fact a branching random walk representation. So this psi n of zt is our log determinant, or the center version that we want to understand. And then I claim that this is a branching random walk. And in the real case, additionally, we find a new interesting connection of random matrices with inhomogeneous branching random walk. So this, again, I'll show you in the next slide. And then one thing I want to say is that behind the proof of the fact that this is a branching random walk, there are many technical difficulties, and in particular, fundamental input is the correlation estimates for this trace of these two resolvents at different z1 and z2. Basically, one has to show that if z1 and z2 are sufficiently away from each other, so by sufficiently away, I mean more than n to the minus 1/2, which is the fluctuation scale, then this is more than it looks like. And in particular, these correlation estimates will be used exactly to estimate the covariation of these two Brownian motions for different z1 and z2. So let me just briefly explain why this is a branch random walk and why we see the emergence of an homogeneous random walk in the real case. Okay, so after many technical steps, one can see that, as I said, that this is in fact a branch random walk representation in the following sense. So if we look at the correlation of this yk for different z1 and z2, then and see if the z1 and z2 are close to each other, by close is dictated by this time scale tk, then they are almost asymptotically perfectly correlated, just proportion given by the variance. On the other hand, if the z1 and z2 are far from each other, then they're asymptotically independent. So this is exactly the branching structure that we have seen in the very beginning of the talk for branch unknown walk, and they are all asymptotically after we have this representation. So, and now I want to conclude by trying to explain the difference of these two fields in the real and in the complex case. Why we see that in the complex case we have an homogeneous branch unknown walk appearing, in the real case it's inhomogeneous instead. And this is because the underlying fields are quite different. So in the complex case, if we look at the correlation as we've seen before in this result by Ryder and Virag, if you look at the correlation for different z1 and z2, then this is given by the log of the difference of these 2 points. On the other hand, in the complex case, there is an additional term. So we have again the same term, which appear in the complex case, but there is a term which also is the log of z1 minus z2 bar. So one can see the field in the real case as the sum of two independent, the sum, independent, but like the sum of two different fields. And this, it's manifestation of this fact that I mentioned a few slides ago, that in the real case, the spectrum is symmetric to the real axis. So that's naturally what you would expect, that if you expect a correlation close z1 and z2, it's also natural that also a term with z2 bar appears because of this symmetry. And in fact, this is the reason why we have these two different behaviors in the real and the complex case. So in the complex case, if you look at the variance of this ykz, is always, for every case, log n over 2. So we just have a homogeneous branch in unknown walk with this yk variance log n over 2. So it's like at the beginning. However, in the real case, the situation is different because at some point, for some value of all case, there is an abrupt change. So there is a k0, which is defined as follows, that if k is small, then the variance is log n. So because each one of them contributes, each one of these two terms contributes log n over 2. But then at some point, one of the two terms doesn't contribute anymore. So we get an abrupt change from log n to log n over 2. And this change depends on the imaginary part of the z that we are looking at. So this shows why, this difference in the variance shows that, well, if the imaginary part is 1, then there is basically no change. So these two are basically the same, modulo a few k's. But if the imaginary part of z is small, we do see a difference. And this is exactly what this inhomogeneous structure is what gives this atypical behavior in the real case, so that if you look at the maximum over any mesotropic slice, then it's always the same, doesn't depend on the alpha we're looking at. So yeah, this is just a summary, and maybe let me just conclude. It was already quite a long talk, and thank you for the attention.
Thank you very much, Giorgio, for a very, very nice talk. Maybe you could go back to your summary page, and people could maybe ask questions if there are any questions. Are there any questions for Giorgio?
So I have a question. Yeah, I mean, it's more a comment than a question. So still, always in all of these results, the main technical input is to compare with the Gaussian is to find out the branching structure, right?
Mm.
And somehow that makes kind of difficult the proof, because actually the branching Brownian motion is already a complicated process, right?
That's right. Yes. Yeah, indeed, it is. That's also why. according to how precisely you want to know this maximum, like you have to have a better and better understanding of this branch and walk, because I mean, it's only true asymptotically. And so yeah, it gets more and more important. For the first order, it's okay, but like for the second order, there are already many difficulties. So I mean, I think, yeah, one needs to start to introduce barriers, arguments, and things like that to show that basically you have to condition that this branch and the work cannot be too low or too high, and so on. So it gets quite nasty. Thank you.
Could you go back to your main theorem? I think you had a couple of main theorems, but let me see which one.
So this or the
Yeah.
previous one? This?
Yeah. So this is also in distribution, or
Yes, yeah, we proved it in distribution, but like with a bit more technical effort. I mean, I'm sure one can prove it also pointwise. We didn't do it, but like it can be done.
And I just had a minor question about the difference between the real and the complex. You had, I think,
Yeah.
some variance expression. Yeah. So
maybe,
no, that one you just showed.
sorry. Yeah.
Sorry. So do you have more eigenvalues in the complex case in this strip? You know,
No,
alpha.
So the number is the same. The point is that in the complex case, the variance of this log determinant on each, say, for each z, it's smaller than in the real case. So that's why you have the maximum is smaller, because I mean the maximum in the complex case you can think that is basically just a union bound. So you have like less points, since we are looking at a region that has a smaller volume. So that's why it decreases with alpha. Instead, in the real case, it does not, because even though you have less points, because of what I showed in the last slide, is that on each point, the variance also grows with alpha. And it happens so that the increase in the variance is done, designed in such a way it precisely compensates the less points, so you get still the same answer. But I don't know if there is a good reason for that, or it's just a coincidence. I don't know.
And the next order term, I guess that's part of the conjecture, right?
Yeah, it's expected, at least on this global, I mean, if you take the maximum over the whole thing, one would expect to be, again, the same. But I mean, we are working on this, but it's quite technical. I mean, it's unfortunately it's quite involved. In fact, I mean, this even in the complex Gaussian case, this is not known. Even where you have explicit formulas, this is not it's not computed.
So what I think from the beginning of your talk, the suggestion was that if you can compute the maximum, you get an expansion like this. You see the 3/4. Therefore, you have a strong suspicion that the underlying field is log correlated.
Yeah, so I mean, yeah, that it falls in this universality class, so the same universality class of the branching Brownian motion and so on, basically. Yeah.
Okay, but that correspondence, there's no chance to prove that, or.
What do you mean? I mean, like, so that this is log correlated. I mean, one can show. I mean, it's like say this kind of research that the log determinant is log correlated, but like then yeah. So like the first step is to find something that's log correlated, and then check on the side. Yeah, for look at the maximum, or like say this exponential measure and show that it's basically the same as for the, I don't know, CFT or benchmark motion and so on. I mean, there is quite some work from several different people in this direction, but it's still, I mean, because you have to work with this high points and so on, like exponential measure or maximum, it's quite delicate, because, I mean, there are like low probability events, basically, that like still governs the thing, because it comes with exponential probability. So I mean, I think in the next few years there will be further progress, but like it still takes some work.
Okay, thank you. I can ask you offline. But other questions? Okay, well, if not, let's thank Giorgio for a very nice talk. Thanks, Giorgio. Thanks for coming on.
Grazie, Giorgio.
The chance to talk.
Yo.
Mhm.
Yeah, great, Giorgio. So yeah.